Hello! Today I will tell you a story about how ScyllaDB is squeezing the most out of its storage engine with state-of-art compaction. A little bit about me. I worked in the past in a couple of projects like OSV and now ScyllaDB. That's enough about me. Let's move on to the interesting part. Okay, so I would like to start with this great quote. In order to make good use of computer resources, one must organize files intelligently, making the retrieval process efficient. This is a great quote from this paper written in the 70s. Of course, the choice of good file organization depends on the kind of retrieval to be performed. Database programmers have been working on storage engines for many decades already, since the 70s, where many papers were written on the topic. This is a great, short and precise definition from the aforementioned paper about what a storage engine is. It allows users to store, update, and recall data. There are two approaches for handling updates in a storage engine. One of them is in place update structure, such as B-tree. In this example, each entry contains a key prefixed with a K letter and a value prefixed with a V letter. In-place update directly overwrites old records to store new updates. K1 is updated in place. This structure sacrifices write performance, as updates translate into random I/O. Also, consecutive updates and deletions lead to fragmentation in the index pages, reducing the space efficiency. The other option for handling updates is out-of-place update structures, such as the LSM-tree. Same scenario as before, we want to update K1. Out of place structure, always store updates into new locations instead of overwriting old entries. Immutability is the main attribute. This design improves write performance since it can exploit sequential I/Os, allowing for faster update ingestion. The major problem of this design is that read performance is sacrificed since a record may be stored in multiple locations. For correctness, the latest version of the data is returned on the read path. It requires background operation, what we know by compaction, to reorganize the data incrementally in order to improve storage and query efficiently. So I would like to say that out-of-place update is not new. In the 70s, a paper called Differential Files shows its applicability in the real world. The paper explains very well the higher level concept behind LSM. When writes are slow, defer them and do them in batches. A differential file for database, this is actually a good analogy that's presented in the paper. A differential file for database is analogous to a errata list for a book. Rather than print a new edition of a book each time a change in the text is desired, a publisher identifies corrections by page and line number, collecting them into an errata list, which is distributed with each book. This procedure significantly reduces the publication costs. So the LSM-tree paper, the official one, was published in the 90s, in 1996 to be more precise. It addressed many problems with a merge process, which is integrated into the structure itself, providing high write performance with bounded query performance and space utilization. In the original LSM-tree design, it contains a sequence of components, C0, C1, up to CK, where the C0 resides in memory, whereas all the remaining components will reside on disk. Incoming writes go to a memory table, which is C0, and once it's full, it's merged into C1. When the on-disk component C1 is full, it's merged with C2 and so on. This merge procedure, also known as compaction, is crucial for efficiency of queries and space utilization. The paper also demonstrated that under a stable workload, where the number of levels remains static, the write performance is optimized when the size ratio between all the adjacent levels are the same. I would like to say that this principle has impacted a lot the implementation of Cassandra and, of course, ScyllaDB. So one of the good properties of LSM-tree is how it simplifies concurrency control and recovery. And that's done because multiple disk components are merged together into a new one without modifying existing components. It simplifies a lot the crash recovery. If the database crashes in the middle of a merge, all the components will be intact. Crash recovery can just discard the partial components. And modern databases such as ScyllaDB implements the disk components as a run of SSTables. Now for the read path, the life of a query on LSM-tree. It will search all the components, which includes the memory table and all SSTables sitting on disk. And of course, it has to reconcile the results. That is, to find the latest version of that key. In this example, the query on K1 reads the key from both memory and the disk component and returns the record with the most up-to-date information. The shape of now about LSM-tree compaction policies, which is how to drive the shape of LSM-tree. It determines the space and read and write efficiency for the database. Therefore, the policy has to be carefully chosen based on the workload requirements and performance goals. The policy is composed of four primitives. It's basically, like I said, it drives how we are going to do compaction in the LSM-tree. So it has four primitives, which is the trigger, file picking policy, the granularity, and layout. The trigger is about when to compact. The policy is which data to compact. The granularity, how much data we are going to compact at once, and the layout, how we are going to lay out the data on disk. Tiered and level are the most famous compaction policies. In the original LSM-tree design, there is only one disk component per level. One of the problems with that is the write stall. Database stops accepting writes until C0 is merged into C1, which is the first disk component, to avoid running out of memory. This compaction policy was implicitly assumed when people talked about LSM-trees, which is the peer-leveled policy, which is implicit in the original LSM design. To avoid write stalls, modern LSM-trees implementations are more flexible with fixed level policy. They allow more than one component in the on-disk level, and that's done to reduce the write amplification. And in-memory component is not merged with a pre-existing on-disk component, but rather flushed into a new adjacent component, which is on disk. That allows the write stalls to be reduced because we reduce the write amplification, the write cost to flush the memory table into the disk. Once the first level reaches its capacity, which is defined by the size ratio of the adjacent levels, the level is merged directly into the next level. No flexibility from level 1 onwards. The input data is only removed on successful merge completion to guarantee is crash recovery, which we talked about previously. Now it's very important to talk about this partition optimization for level that came later in time. It's basically about people realizing that merging entire levels, which is known as full merge, is problematic. So the idea is basically about partitioning the data in each level, each LSM-tree component, into fixed size fragments. So when compacting, we are not going to do the full merge, but instead we are going to do the partial merge. And this technique allows compaction to have bounded operation time and temporary disk space. That is the amount of disk space required for compaction to complete. Each fragment is represented in practice as a SSTable, which is sort of string table, the default file format used in ScyllaDB and many other databases implementing LSM-tree storage engine. So each level now has its data partitioned into SSTable files, which don't overlap at the key range. There is no longer a single component per level, but rather many components that can be logically treated as a single one. When level 1 exceeds capacity, a single file in level 1 can be merged with overlapping files in level 2. This partial merge is what bounds the operation time and the temporary disk space required for the compaction to complete successfully without running out of disk space. And this is the cost analysis for level policy. For leveling policy, SSTable at a given level will be compacted t minus 1 times until the level fills up, and that SSTable is merged into the next level, where t is the size ratio between the adjacent levels. The worst case occurs when all the data when all the data at all but the largest level, which contain approximately 1/10 of the total data, are updates to the entries at the largest level. So that's the worst case for level policy. So later in time, after the original LSM-tree paper was presented, a new paper written, published in the 90s, a few years later actually, introduced a new approach to the LSM-tree layout, which was about the actual difference is that it allows LSM-tree to have multiple in these components per level. So it trades off space for write efficiency. So, quoting the paper, the goal is to design a technique that supports both insertion and queries with reasonable efficiency without the delays of periodic batch processing. And that gives birth to the tiered compaction policy. So that's how it works. Over time, new SSTables are created on the first level on disk. The tiered policy allows accumulation of k SSTables before merging them into the next level. This k parameter can be usually controlled by the user, and in ScyllaDB it's referred internally as the threshold. Compaction takes place by reading those SSTables from disk and performing a k-way merge on them. The k-way algorithm is made possible because the SSTables are sorted on disk, so we are able to iterate them through the input SSTables in compaction incrementally applying this technique. And finally, the output of the merge is written into a single large SSTable that will belong to the next level. Of course, assuming very few to no overrides. For tiered policy, SSTable at level 0 will be compacted L minus 1 times until it reaches the last level. The worst case occurs when the updates to the keys are redundantly stored across all the components of disk, meaning all the updates to a given key, but the last one are erased in disk space because it's the updates are redundantly stored across the components in the tree. Very important policy for write-heavy workloads and updates, and when updates for key are not so frequent, allowing the read and space efficiency to be reasonable. Now the ScyllaDB journey begins. The database inherited all the LSM-tree improvements described so far, but turns out they were not enough. As explained previously, the input files can be only released on compaction completion after it succeeds. Therefore, the temporary space overhead for compaction is the size of the input data, given that the output can be as large as the inputs. In the worst case, the space requirement is the size of the data set size, so users of tiered policy are forced to leave 50% of free disk space. This makes it very, very expensive in terms of storage density. What can we do about it? Remember the partitioning optimization applied for level? Turns out we can do the same for tiered policy. Partition the data of each. We are going to partition the data of each SSTable into fixed size fragments, allowing the data of each SSTable to be incrementally released during the compaction process, not after. When compacting the SSTables in level 0, we will release the exhausted fragments of input SSTables as soon as the data is safely stored in the fragments of output SSTable. With this approach, temporary disk space is now bounded by the fragment size, not the dataset size. So it bounds the temporary space overhead like it was done for the leveled policy. It allows the disk space to go way beyond the previous limits that haunted us to 80% and beyond. It's available in ScyllaDB as incremental compaction strategy. You can read more about it in the documentation. Is that enough? We didn't think so. So now let me represent the efficient space of LSM-tree compaction policies as a grayscale spectrum, where the space efficiency is on one side and right on the other. I'm leaving read efficiency out for simplicity. It's not strictly needed for what I'm going to explain next. At one side of the spectrum, you have pure leveled, which brings most of the space efficiency while sacrificing writes. At the other side, you have pure tiered, which brings the most of write efficiency while sacrificing space. But, you know, the world is not black and white. There are shades of gray in between. So we came up with a new hybrid LSM-tree data layout, which is a result of combining properties of those two leveled and tiered policies, something in between, therefore a hybrid approach, where the largest level is space optimized, it's going to behave more like leveled, and the others are right optimized, more like tiered. It addresses the okay space amplification in tiered for override intensive workloads. When compacting all levels, but the largest one, the behavior is exactly as in the tiered policy. For example, two SSTables level 0 are written to a new SSTable in the next level. Unlike leveled, no merge is done with the pre-existing data in level 1. The story is different when compacting to the largest level. Leveled mode kicks in. SSTable in the second largest level are merged with the data with the single SSTable in the largest level, which is a single SSTable run, exactly like in leveled policy. This hybrid approach will allow compaction to dynamically adapt to the workload. So we have a hybrid plus dynamic behavior for this module. It dynamically adapts to the workload. Under heavy write load, compaction works to meet the write latencies. Otherwise, it optimizes for space efficiency. Under low write load, space efficiency can be almost as good as that of pure leveled. But as soon as the write load becomes heavy, the policy optimizes for writes, seeking a write amplification close to that of tiered, allowing the database to keep up with the write rates to minimize the impact on P99 latency. So hybrid and space efficiency have boundaries on pure and tiered, leveled and tiered, meaning hybrid cannot be worse or better than them, but somewhere in between. The main advantage is that it allows write and space efficiency to fluctuate between those boundaries, creating a new opportunity that those primitive policies were not able to provide. So it reduces space amplification over write-intensive workloads, it's less space amplification, increase the storage density per node, and more money in your pocket. So that's great, right? It's available as a space amplification go option of incremental compaction strategy. Again, you can read more about that in our documentations. Now let's talk about one of the most difficult problems in the LSM-tree domain, which is about handling tombstones efficiently. A little bit of background. When deleting data in LSM-tree, the out-of-place nature is not disrespected. If you want to delete key A, a tombstone, which is a record of deletion, is written, say we want to delete key A. The deleted data will only be purged once it's compacted with the tombstone. Until there, disk space is weighted by both the tombstone and the data it shadows. One of the problems ScyllaDB inherited from Apache Cassandra is that garbage collection happens on a single file of a single level at a time. But I would say that's suboptimal. For example, if we try to collect the garbage on that file on level 0, the tombstone cannot be purged because the data shadowed by it is in level 1. So both remain on disk until they are merged by a regular compaction procedure, which can take an indefinite amount of time. Not having an efficient garbage collection approach means that not only space efficiency is reduced, but also read efficiency because the database will have more work to do during the read path. With that in mind, Scylla now implements a garbage collection that can merge data across level to allow tombstone to be purged more efficiently and quickly. It piggybacks on incremental compaction to make sure temporary disk space is bounded, allowing this cross-level compaction to take place without running out of disk space. We have gone beyond the improvements available in the literature, and we intend to keep improving our storage engine. Thanks a lot for listening, and have fun in the Scylla Summit. Bye-bye.